Hi all, Mads Barnkob here from Kaizer Power Electronics. Welcome back to part 2 of building the 10-minute design DRSSTC. This Tesla coil build is going to take a little bit longer than first imagined. Since part 1 I have been building a little bit here and there, and this video will be pretty much looking at what I constructed so far, how I did it, how easy I think it is, and hopefully I can teach you to do it as well. And we will just progress so far that we would have all the finished parts, probably not getting to the point in this video where it's all operational, but we should have all parts at a point where it's simply down to wiring, I would say. If we could get to that point here in part 2, I would be happy, because then I would finish the wiring, which is just more like, following a schematic. Let's dive into what have been made. The work table quickly becomes a huge mess. Here I have been trying out how much space would I have inside a wooden circle of 30 centimeters. So I would have a heatsink here. I would have the PCB here, the 6 electrolytic capacitors, a power supply, which probably is a bit too large, but maybe it can be there, I don't know. And we'll have to fit the resonant capacitor somewhere as well, and standoffs for the upper platform, and some sockets and stuff. And inside this black box we would have the driver itself. It's just a matter of how tall do I want it to be. The gate drive transformers have also been made. There is 2 for each coil. And I made a video about how to make gate drive transformers, so just to check the link out in the description for the details on making these. And the same goes for the current transformers. They're not complete yet. Yeah, the main part where the primary wire goes through, and it has to loop through the second for the cascaded one here, and we'll have a 1 to 1000 ratio current transformer here. Another thing I have been working on so far is the bus bar, the DC bus plane. And this is just made with a multi-tool and just routing off the copper layer here. So I didn't even spend time on etching it. It was easier to make these 6 monkey faces, it looks like. So here I will mount the electrolytic capacitors, and then it can mount directly from these 2 holes here to the connections on the full bridge PCB. The MMC capacitor is finally here. So we have a nice little box here. So this turned into an unboxing video as well. So let's see what that looks like. Oh, they're huge. Much larger than I expected. Oh, and they even came with some mounting hardware. Well, that's nice. So I would say that just from the weight alone, I still doubt the 80 amp RMS current handling of these. They are simply too lightweight compared to others I have that are rated at 60 or 50 amp RMS. But I don't think we will kill these in a Tesla coil like this. So for sure it takes up a lot less space than building one from the Cornell Duplier capacitors. Let's first construct the bridge. The DC bus plane, I have soldered up the through-hole stitching here. So I'll stitch the positive side to the positive plane, and I have routed or grinded off the connections over here, and I have left the mechanical fixation points here, which are needed for the capacitor, and then we have the negative side sitting on this plane. And with the capacitors soldered in place, it looks like this. So a nice little heavy bank. I made sure there is enough space for me to mount some screws down between the capacitors there, so I can use standoffs to mount it directly up to the PCB for the inverter. Next step after completing the DC bus PCBs and soldering on the capacitors would be to fit the full bridge PCB on it. Now I chose these large 2.2 microfarad snubber capacitors, but they're simply taking up too much space. So I'm going with two smaller ones, which is half the height. And then it's not 2.2 microfarads, but 0.47 and 0.1. But I think that will do with the low inductance design that we after all do have in these short connections. The connection between the DC bus and the PCB is just made with brass standoffs, like that. Screw through, and then with mounts, it's hard to see here, in between the capacitors where I can connect the wires with the DC voltage from the rectifier. So the next thing to do here would be to fit the IGBTs and somehow get these hacksawed heat sinks. Mark up where to mount it in the heatsink. Solder only one or two legs of the IGBTs just to get it in place. Because with this one where I have mounting holes, that is not a big issue, but the other heatsink, which uses these clamp-ons, that's very hard to mount when working with something sitting here, because I will also have to bend these out a bit, so they will be at an angle compared to the ones here that can go straight up. Actually, I can see it will have to bend a bit because this is not the same thickness as the distance between the two rows of IGBTs. And found some blowers to mount on the heatsinks as well. Also located some flex copper bands. These are very good for high RF current, as this is multi-threaded, so the RF current can really flow on the outside. Skin effect is no issue with this. And you can argue that these pre-made with holes are expensive. Well, this is just the shielding out of a motor control cable. Regular three-phase control cable you can buy and find very cheap online. This is just the shielding pulled out of it. Then just made flat, and you can poke a hole in it and then use this. Just as good as the other pre-made ones here. So that's the progress so far. I will get some more soldered, and the next thing I think we will have a complete bridge and try to arrange everything in this circle and see if we can make it fit. It is time for an update. Quite a lot of new things has happened since the last build update. Well, just a few seconds ago for you. But I have been building parts of the Tesla coil for the last 2 to 3 weeks since the last video with the start of the building. And Bjarne the kitten has joined Kaizer Power Electronics, as you can see, and he is quite adventurous and probably a very bad idea to have around the sensitive parts here. Whoa, Bjarne. Quite a lot of the plan has been just as I wanted, no issues there. But one of the major setbacks was the primary coil. That it was simply, I think I got scammed on that one. Ordering copper coils on eBay is probably not the best thing, unless you know it's a reputable seller. Turns out it's magnetic, but we'll look into that. The secondary coil and the connecting part here, the bottom connector, and it also had this acrylic disc. Well, I just assumed the acrylic disc would go in the top here, and no, it simply does not fit. But the holes in the acrylic disc here corresponds with the holes at the bottom here, so I assumed it's just a back plate for mounting on the other side of a base plate. So I was lagging some way of mounting the top load up here. And that is fortunately quite simple to make. You find a similar sized pipe So this is also from a 75mm pipe, and you make a cutout, and then you can just press it together and glue it in here with regular glue that can do plastics, PVC. And then I cut out a small disc with a 73mm hole saw, which is pretty standard for electrical installations in Denmark, so I had that ready. And as you can see, that fits nicely down into the pipe here. Very nice fit. I had some brass standoffs, and I want to keep all the high voltage out of the inside of the secondary tube, because that's just bad practice. You will risk having flashovers on the inside of the tube. So this will be used to connect the secondary coil wire underneath here, and the brass standoff will be enough to just leverage the top load the right distance from the top of the secondary coil. It is absolutely perfect. There's something like maybe half a centimeter between them. So that is just fine by me. Mounting the top load with the brass standoff here is going to be quite nice. So we can try it out here on the coil itself that is getting assembled first. Now I have not yet finished the wire going up with a lock underneath here. But it would simply be like this, and we can add the two halves of the top load here. I think you would agree that this is a nice looking setup. Maybe a centimeter too tall for the top winding of the secondary, so we will lose a bit of field control for the top winding. We could add a brass tube up there on the top if it becomes an issue with corona. But generally, that is not something I have experience with, that it becomes a problem. But yeah, quite simple to mount the top load, and the electrical connection is just fastening it to the brass standoff. The making of the primary holders follows a pretty simple pattern. We have a set distance to the secondary coil where it starts. From here on, we have, or I decided that I have 4 holders because that makes calculation easier. That here I simply have 1 centimeter apart per winding, and I have to divide this into 4 turns or 4 different holders, so that would be 2.5 millimeter that I have to move this pattern on each of the holders. Illustrating that on a drawing that you can see here, that the different start points, that it simply just makes these rows. And eventually we will, of course, need the 6th, where the 5th turn ends, as you take a 1 full turn to have 1 turn. So you need 6 on the first and then 5 on the following holders. This file will be available on the website and forum as well. Alongside showing you the parts here, I will also show some pictures on how this was made in the workshop. It is simply just drawing up the square here on a piece of acrylic and drilling the 6 or 5 holes plus the one for the strike rail. It's quite easy to just make out all the parts that you need, and it's just sawed out with a regular handsaw. Working with acrylic, you need to be very careful and use low-speed tools only, and that is why a regular saw is pretty good to saw it, because it has large teeth. And when drilling, you have to drill at low speed as well, because acrylic simply just starts to melt. So you have to work slowly, pull the drill up often to get rid of the material that you drill out, so else it will just start being driven around and melt and turn into a puddle and ruin your nice clear acrylic. It will turn white and start boiling and melting. So can quickly become ugly if you do not watch your speeds when sawing and drilling in it. Here we have the full bridge rectifier connected with 2 wires to the standoffs sitting on the DC bulk capacitance here. And that fits nicely with the standoffs needed for the bridge itself. So the idea is that it goes here. And that could probably be smaller. No one brings a kitten unpunished into a workshop. So he jumped up on top of my Tesla coil here. The top load was not securely fastened and it tipped over. So that was the loud noise you just heard, where I were almost through the bridge across the workshop here. It took quite a lot of damage, as you can see here. A huge dent into it, made a hole, and then it continued down and hit the floor and took another hit here. And it has a previous fall damage on the other side here as well. Yeah, top loads are not made to be the most sturdy part of a Tesla coil, so they certainly don't tolerate being thrown around. The double standoffs here were not needed on this bridge, but it's needed on the other bridge, because here, due to the heatsink method, the capacitors are on the back side, and unfortunately just large enough that one stud here is not enough. So that has to go in here like this, and here we can see that we actually need the room from it. So I think I will just make them identical, but I could also just mount these wires from the back on one of them, but I could also just make them identical. The 2.9 driver actually has a thermal contactor input. And I happen to have these 17 degrees normally closed switches that once these reach 70 degrees, they will open the circuit and that will shut off the driver. So I have lots of these from various teardowns, so I thought, why not add them to the heatsinks and try them out now that the driver has the possibility. Having made the primary holders, I was about ready to fold the primary coil. I took it out into the workshop, and by accident there is a magnet on my work desk. And, well, this is copper coil, clearly. This is a magnet. And this is not copper coil at all. My best chance is it's a nickel copper brake line, which is available. Nickel still has 4 times the resistance of copper, so even by that measure, it's unusable for a primary. I tried scraping the surface and it comes off very fast. So it's a very, very thin layer of copper made on the surface of the tubing. So I just had to go out and buy something different. And I think it would be funny just to listen to the sound of it. That has a very sharp sound to it. Whereas real copper coil has a real soft sound to it. Winding coiled copper tubing into a primary coil is not a guaranteed success. So in order to succeed, we can do some things easier for ourselves. Something like wearing gloves, because we need a firm grip around the copper tubing, and also not to stain it with the acid that you have on your fingers. That will leave some ugly marks on the copper tubing. Other things we can do is that the diameter that this comes in, as we can see, it is a much larger diameter. And if we just bend this by hand, we risk kinking it, that it simply gets a sharp bend. So what we can do is use something with a diameter nearer what we are needing, and we can coil it around this tube to start with, to get a starting point. I will wind this primary in the clockwise direction, but generally it doesn't matter, because you will just have to change the phasing of either your feedback or the primary connections from the inverter. Direction is not critical. I coiled up the first 3 turns around the tube, and I bent a 90-degree start connection here, which goes down to the resonant capacitor. I drilled a hole near the first holder here, as we can see here, and this is the start of our primary winding. And it goes into the first slot here, and we have a piece underneath for the connection to our resonant capacitor. I drilled small holes underneath each slot in order to be able to secure it, not with zip ties, but with some copper wire in the end, because that can withstand some heat. But now it's simply just a matter of manipulating the copper tubing into a minor diameter, and this can be a bit tricky to not, as I mentioned earlier, kink the wire or kink the tubing too much, because this is a pretty narrow bend in the start, and I did not choose a pre-bending form that were just like this. But just keeping my finger on the previous turn here, I think we will pretty quickly come out to a diameter much more like the one from the orange tubing. Or maybe I will regret not securing this as we go. At least it will never get as bad as when I winded a helical coil through acrylic plastic. That was a royal pain because it kept locking up. And the uneven distances between the turns here we will have to deal with a little bit later, I guess. Well, this is a good example of it doesn't have to be perfect because it's not getting perfect. Like that. And okay, so now it starts to get a bit easier. I could, of course, also have cut off the excess length that I know I did not need. You can see it's starting to look like a actual primary coil now. And of course, maybe securing the form itself without just balancing it on top of something else would also have made it easier. So we could have done a lot of things in order to make this easier, but I wanted to show this quite raw on video, step by step, on how to wind it. And then by not fastening it, we can tighten it up a bit afterwards. I can also see now that the slots in the primary holders could have been a bit deeper. So in order to actually keep the coil in place. And that's the last one. We're back at the start. The primary coil is done, and I secured the first one with this 1.5 square millimeter stiff copper wire from normal house installations. It left quite a sharp cut here where I cut the wire after twisting it. So I think this is not quite good. I need to add a large solder blob in order to avoid any corona on this one. But let's check out the other primary. I used a much thinner wire here, and as we can see, it leaves very little sharp edges here. But it's still something that I need to patch up with a solder blob in order for avoiding corona. But I think the thinner wire here, which is still just tinned solid copper wire, is a better solution. So I would definitely go with that. But we will see the performance of these two different methods of bonding the primary coil down to the holders. For the primary circuit wiring, I introduced using these pre-made flexible copper braided bands here, but they are a bit long for the small distance I have. So I went with the braided copper shield here from Motor Control Cables. Just cut it off and soldered it, and then punched the hole with a screwdriver. I made the two small pieces here from the bridge to the resonant capacitor, and then the back side of the PCB facing furthest down to the bottom plate have to go the other way. And here I put it into a flexible rubber tube or just protective sleeve here, as it will pass through the whole coil assembly and past the other electronics. And then we can also use this when we have to mount it on our current transformers in order to secure them or isolate them a bit more against the high voltage in the primary circuit. Speaking of the current transformers, I mentioned that these could be optimized, and I didn't think of this in the start of the video. But here we can see that we simply have one where this will pass through the primary circuit, and then a single wire from this passes through the two others, and we have two outputs. And we also have a cat tagging stuff here. All the wiring between the thermal switches and for the AC connections and to the power supply, I actually found all these from various teardowns, so it's actually nice to be able to reuse almost everything that I have taken apart from various power electronics. So just something as simple as these double shoot connectors here. I can connect two shoes together and then just connect it to the bridge, which we have here. And by that, it's pretty easy to assemble two wires into one terminal. Very nice. I had the pre-assembled driver from earlier, and I assembled the second one. Now there's a certain flow you can follow to make this easier for yourself. First, I will mount the diodes and resistors, then I will mount the sockets, then the capacitors, then the larger capacitors, then the sockets or the terminals, and then capacitors, and at last the transistors. By this method you can always just put in your components and turn it upside down, because you are adding layers of taller and taller components. Then you don't have to worry too much about components falling out or not being totally flat against the PCB, so it just makes assembly easier. And we are at a point where everything is stacked on top of each other. Nothing is bolted together, so this is just balancing, so I don't dare touch it. It will just tip over. Let's get closer and look how it is arranged. And I also think this is nearing the end of this part 2 of building it, that the next part will be more about the wiring and testing the driver, because we didn't even look into how to start up a driver, how to do the initial testing and verify that the various parts of the drivers works. So that will be in part 3. I really think that the overall look of this just turned out great. That the dimensions of it is just perfect. There's a bit much space around the base and to the primary coil, but that has more to do with me not wanting to cut into the pipe where the secondary is winded on. But we can now remove the upper platform and secondary coil on top load here, and we can get a look into the electronics. Here I have the driver enclosure, and we can just remove that. Put the legs down here. In the middle I will have the DC board capacitance and the bridge. There's a fan over here for cooling both the MMC, which we're sitting underneath the platform over here. To cool that, along with the heatsinks, we will have the 230 volt AC input over here, and then we have the 24 volt DC power supply in the rest of the space, what is left over here. Thank you for watching. I hope you are getting just as good progress in your build as I think that I am. So until next time, see ya.